great pleasure to have Professor Darren Cziczo here from MIT today, and I want to thank Josie and the Marine colleagues who made it possible that we got him down here for a seminar on Friday. A little bit to his CV from Dan. What I didn't know, even though I know him for several years, he got his BS in aerospace engineering in '92 at the University of Illinois in Urbana-Champaign, and then went to the geophysical science department at the University of Chicago and got his master's and PhD degree there. Afterwards, he joined NOAA in Boulder as a research scientist for a couple of years, and then where we also then more interacted, he went to Europe. It's very rare to see a more senior scientist to go to Europe, often it's the other way around, and was a research and teaching faculty at the Swiss Federal Institute of Technology in Zurich with Ulrike Lohmann's group. And after that, he was there for 2-3 years. He came back to the US. He became the director of the Atmospheric Measurement Lab at Pacific Northwest National Laboratories, where he acted for about 2 to 3 years, and then recently we got the call from MIT to become associate professor there. And Dan has also a lot of awards. I name here a few, and several NASA, DOE achievement performance awards, but most significantly, I think he is also the recipient of the Presidential Early Career Award for Scientists and Engineering in 2005. So it's a great pleasure having you here, that you could come down here, give this talk, and welcome Dan Cziczo.
Well, I wanted to start out by saying thank you to Daniel as well as Josie and really everybody for coming out, but just for the invite to get a chance to come down and speak with you and talk at such a great department. You did make me feel a bit old, because when you mentioned 1992, I started to think back how long it's been since I actually graduated, which is a little bit scary. The other thing that I wanted to start by doing was just acknowledge some co-authors. So I'd like to talk to you guys today about the chemical composition of atmospheric particles and how this impacts cirrus cloud formation. This is not a project that I could have done on my own, so there's other folks that I have to name. There's some associates at NOAA, where I did my postdoc, and I've continued to work with these folks, primarily Carl Freud and Dan Murphy. GK, a postdoc in the group at PNNL. And then also the folks that were involved with this aircraft research program. I'm going to talk to you mainly about measurements from an aircraft platform. So the NASA B-57, both the pilots as well as the folks that keep the plane running, the ground crew, and then also NASA for the funding for this. So this was a study that I did in a transition after leaving DOE, but before starting at MIT, and I'll go through sort of the timeline of this, but this is a study that we did early in 2011. So I realized this is a bit of a diverse audience, that there's some marine folks as well as atmospheric folks in here, and I wanted to try to find a balance, but give a few statements on motivation and context, why I think that this is something important, some work that we should be doing right now. I then want to tell you a little bit about the methods. There's a lot of instrument development work that went into this. I'm actually rather proud of that, and I'd like to sort of show off some of the toys that we built. I'm then going to talk about the field study, which is the mid-latitude aerosol and cloud properties experiment. A bit on the results and discussions, and then finally we'll just throw up a quick slide for conclusions and try to get you guys out of here before it gets too late in the day. So I'm going to start with motivation and context. I did want to mention that this horrible name, Mid-Latitude Aerosol and Cloud Properties Experiment, is MacX, so I'll try to use that acronym from here on out. You guys probably know how much NASA likes their acronyms. So let's go ahead and launch into motivation. So really, we're after the climatic importance of cirrus clouds and how particles fold into that. And one way I'd like to motivate this is from the most recent Intergovernmental Panel on Climate Change report. Everybody's probably familiar with this one. It's the one from 2007. There's a new version due out. This is the one that actually won the Nobel Prize. And what's often pointed out is the warming due to the greenhouse gases. So what this plot does is, on sort of the y-axis here, these are the different anthropogenic man-made forces that have been put into the atmosphere and Earth system. And things that fall to the right of this line here, things that warm the environment, things that fall to the left are things that cool. And what I think everybody pretty much knows about is the large warming potential of the greenhouse gas CO2. A few less people know about methane and N2O and the halocarbons, which are also warming agents, and these are large and positive. What's less well understood is that there's things that actually, that we're doing to the climate system that cool, and those are the direct and indirect effect of aerosols. So the direct effect is how aerosols scatter radiation back to space before it otherwise makes it to the surface. And the indirect effects are how aerosols can participate in cloud formation, and those clouds tend to reflect, again, radiation back to space that doesn't make it into the Earth system. If you add everything up, you get this large positive warming forcing. But you'll see that there's this large error bar here associated. It's not our lack of understanding of CO2 or the other greenhouse gases. This uncertainty is due to aerosols and aerosol cloud effects. That's what's leading to our lack of understanding on how much climate is changing. So I'm an experimentalist. I like to measure things. So I like this paper. I like the report from the IPCC, but this is largely based on modeling studies. So I like things that I can get out and measure. And that's why I like this paper by Dan Murphy and Susan Solomon. What they did was they added up the combined forcing of what we know we've put into the atmosphere, the measurements of these greenhouse gases versus time. So this sort of starts out, it pretends time starts in about 1950. And you can see this big positive forcing again of CO2, methane, and the other greenhouse gases. There's a little increase in solar over the same time. And then what Dan and Susan did was they took this same plot, they took this line of what we know we've put into the Earth system, and they subtracted out what we know we're warming. So we know that oceans have warmed slightly from buoy data. We have satellites that look down at the planet, and they can see that the planet is radiating at a higher temperature, that the Earth itself is a little bit warmer. So you see that here. We know that volcanoes have taken some energy out of the Earth system. They put aerosols into the upper reaches of the atmosphere, and radiation isn't able to make its way lower into the atmosphere that otherwise would. So I always get these wrong. I think this is Pinatubo here. This is Cziczo here, and this is Arung, if anybody remembers that one. But what you'll notice is that there's this big white area, this big sort of unknown area that they use to make this fit, to take up all of the radiation that's gone into the Earth system. We don't really know where it's gone. And what they point out is that this is likely these aerosol indirect and direct effects, so how aerosols are participating in the climate system. It's quite interesting because if you take these measured quantities, this measurement right here, it equates to about -1 watt per meter squared, which is actually the same value as the report is coming out from the IPCC. So in other words, this sort of adds credence. You have this independent sort of modeling radiative transfer study and this modeling study using global atmospheric models. And they tend to agree that aerosols have this large cooling effect, but one that we don't fully understand. And this is really the motivation behind this talk, is trying to shrink this down to understand this area of this plot better. So I realized to go much further, you've probably heard Daniel talk about this, but that I really need to explain cloud microphysics to explain aerosol cloud interactions. So this is actually a course that I'm teaching now at MIT over a semester. I'm going to try to present it to you guys in about 2 minutes on one slide, so I hope I can do that properly. Most folks understand the fact that if you raise, at higher temperatures, higher than about -20, if you raise the relative humidity over saturation, that you form droplets. You go from sort of this aerosol phase, these particles that are floating around in the atmosphere, to water droplets. So that's relatively well understood. What's less well understood is that as you drop the temperature below 0 degrees C, if the relative humidity is high enough, if it's above 100% with respect to ice, you can have ice nucleation. And initially it forms heterogeneously. It has to form on these special little particles here that I've pretended, that I've symbolized as diamonds. And there's a variety of different mechanisms. These particles can become encapsulated with water. They can strike pre-existing droplets, or they can just have material deposited directly from the vapor phase before ice is made. The spontaneous formation of ice, homogeneous ice formation, actually is relatively rare in the atmosphere. It's relatively hard to do. You have to force the system below about -40 degrees C and to relative humidities in excess of 100%, again with respect to, in this case, I'm sorry, with respect to liquid water. So at this point, you're probably thinking that the speaker has a little bit of an issue here, because for folks that stick a tray of water into their freezer and they end up getting ice cubes out of it, you can say, well, the freezer isn't at -40 degrees, so there's something wrong here. Well, actually there's not. Most of the ice nucleation that we see when you put that tray into the freezer and it freezes is heterogeneous. The tray itself is the heterogeneous nucleus. You never take that tray out early if you're going to make yourself a cocktail and see ice floating around in the middle. It didn't spontaneously form. It forms on the sides. You can think of another analogy. If you go out to a river or a lake, you don't see blocks of ice or icebergs floating around unless they've broken off. They nucleate on the sides of that lake. The mineral dust and the boulders on the sides of the lake are the ice nucleus. It turns out that this is the more common process in the Earth system. This is actually rather hard to get to. This takes a lot of forcing. So when we think of clouds, warm clouds on a summer day formed by this mechanism. Mixed phase clouds formed by these two mechanisms here. And cirrus clouds, the ones we're going to talk about today, form either heterogeneously or homogeneously. And we're going to try to figure out what these particles here are and how often this homogeneous process, this difficult process is. If we think about this in sort of phase diagram space, we can map out this concept of ice supersaturation. So this is a relative humidity of 100%. This would be 160%. Versus temperature, so getting colder as we go this way. Cirrus clouds form in this area of the phase diagram. And we can think of the atmosphere as doing something like this, a parcel sort of lifting up. And as it does so, it cools and the relative humidity goes up. So we sort of move through these different mechanistic spaces, first through this deposition nucleation space into sort of a condensation space, and then finally into this homogeneous space. And some previous folks have wondered, what's the relative ratio of this happening and this happening, and how important are they? So, for example, we could think of taking the Earth system and just adding more of these very special, very efficient ice nuclei, these depositional nuclei. And this is work that my former boss, Ulrike Lohmann, did now 10 years ago. What Ulrike did was she took a global climate model, and she started out with the case where there were very few of these efficient ice nuclei, these efficient heterogeneous particles. And this is a map, so this is the equator, and then moving towards both poles, and then moving up in this dimension. And she's got ice clouds forming kind of rather high in the atmosphere, and kind of predominantly towards the poles, as you would expect, towards the colder areas of the planet. And then what Ulrike did was she took, and she carries aerosols in this model. She made 1% of the black carbon into very good ice nuclei. She just sort of theorized that this was the case. And you can see this incredible increase in ice clouds in the climate system. And then she said, well, maybe 10% of the ice nuclei, or 10% of the black carbon in the atmosphere are ice nuclei. You can see that ice clouds predominate. They're all through the depth of the atmosphere now in the polar regions and high up. And then she equated this to a radiative forcing, how much radiation was able to make it to the surface, and how much was trapped, how much terrestrial radiation was trapped on its way out. And that's plotted here. And what she realized was if you integrate these effects, the effects of this glaciation effect, of this ice formation, was as great as the direct effect, the scattering and absorption of all of the particles in the atmosphere combined. So put another way, in those earlier figures where you saw the radiative impact of aerosols and this large uncertainty, this is saying that perhaps a half of that can be due to just ice nucleation, this glaciation effect in the atmosphere. And this is why it's so important for us to study and understand in moving forward in terms of climate change. So with that very brief introduction as to why we want to understand ice formation in the atmosphere, I'd like to move then on into the methods of how we're going to do this. So our goal here is to understand what particles are forming ice in the atmosphere and see if that can tell us something about the climatic impacts moving forward, how we're changing particles and how they might have an impact on climate. So to do this, the first thing that we have to do is figure out what those particles are. And we use a technique called single particle mass spectrometry, and it works something like this. Particles are brought in through an inlet, and we pass them through a couple of visible laser beams here, green lasers. They scatter light, and this allows the instrument to know that there's a sample there to be analyzed. And it also tells us what the size of the particle is by measuring the time it takes to move this fixed distance between these two beams. We then trigger a second type of laser, an excimer laser. It's the type of laser that they actually do laser eye surgery with. That strikes the particle, and it does two things. It ablates the material of the particle, it burns that material off, and it ionizes it. Once we have ions, we can manipulate these in an electric field, and we just do mass spectrometry on that. So what happens is the lightest ions, the smallest ions, sort of win a race to the detector, and the heavier ones, denoted by this larger sphere here, sort of lose the race and come to the detector sometime later. And we end up with something like this on a particle-by-particle basis. This is a single particle mass spectrum, something that was gathered last year in this field mission I'll talk about. This is the signal that we get, so that you can think of this as the amount of ions versus the mass to charge. These are the lightest ones that are coming in first. These are the heavy ones sometime later. So you can see that by assigning masses to these, 12, 27, 40, we can figure out what the chemical composition of this particle was. So this is something like a mineral dust particle that we saw in the atmosphere. We're sensitive to things from about 150 to about 3,000 nanometers in size, about 3 microns here. Optimal transmission is a little bit less than that. And we believe we have almost universal detection, so we can see almost everything that particles are made out of in the atmosphere. So this is how we tell what the particles are that are forming ice clouds. We have to have a way, though, of separating the ice out of everything else. So these ice clouds, although they sit high in the atmosphere, they have a large radiative impact, they're rather tenuous. There's only maybe 10 or 100 particles per liter of these cloud elements, where there can be thousands of aerosols per cc, so many orders of magnitude more. We're again talking about something like 1 in 10,000 or 1 in 100,000 of the aerosols making these clouds. So we need to separate those clouds elements out with high efficiency. And we use something called Counterflow virtual impaction. It works something like this. This is an inlet that would be on an aircraft. The aircraft is sort of flying in that direction. And there's a flow of gas that's pumped out of the front of this inlet. So when small aerosol particles, the ones that we want to reject, see that flow of gas, they're sort of shuffled off to the side, and they're taken out of the system. We don't see those. Cloud elements, these larger elements here, have enough inertia that they penetrate that flow. They make it into the inlet, and then the flow back here is warm and dry. So you get rid of the condensed phase water, and you're just left with whatever the particle was that formed that cloud. The analogy I like to use is it's a bit like a hairdryer, right? If you stick a hairdryer on the floor and you drop something like a ping pong ball on it, it doesn't hit the hairdryer, it falls off to the side. If you drop a bowling ball on the hairdryer, it doesn't care that there's a flow coming out of that hairdryer, it smashes into it. Okay, we're not trying to smash the inlet. There's an analogy there as well, which I'll get to in a moment. But that's the concept. Now, one of the problems, though, is that these designs were actually originally built for water droplets in the atmosphere, which are relatively small. They're only a few tens of microns in size, whereas ice crystals are much larger. They can be hundreds of microns in size. And there's a large change in mass, as you can imagine. It sort of goes as diameter to the third power. So we actually realized that we had to build a new kind of CVI, something that could separate out larger cloud elements. So we did a computational fluid dynamics study of how to do this. And we came up with this concept of a folded design, which I'll explain in just a moment. We made the flow take a vortex pattern, so you can imagine those crystals have to sort of follow this helical motion. They spend a lot more time being warmed and dried, getting rid of the gas phase, getting rid of the condensed phase water. So this helps out. We use the carrier gas as counterflow instead of just being air. We use neon because it's a higher viscosity and higher thermal conductivity. So you can imagine it's a bit like trying to swim through honey or peanut butter instead of swimming through just water. That's the idea, is it's just making it more difficult for that crystal to get through the flow, taking longer residence time. And then we also pass an infrared laser down the beam of this unit, trying to put more energy onto that ice to melt it and evaporate it. So just as a quick cartoon, the CVI looks something like this. Again, these small particles are sort of shuffled out of the way, and we don't worry about them, they're rejected. The large ice crystals are brought into the flow. I've exaggerated the size. You might wonder how it made it through the inlet. Don't worry about that. It's just a cartoon. So there's this high viscosity flow. This is sort of slowing down the whole way. We've got this laser that's pointing out, so it's absorbing energy, it's melting and evaporating. And eventually it's sort of turned around. It just has to stop at this point here and then traverse back. So this is the idea of this folded design. Instead of just using one pass of length, we actually force that crystal to go all the way back here. It's evaporating the whole way until it finally releases the special particle that was inside of it that formed that cloud that we want to identify. And that pops out, and then it goes down this pipe, and then we do our mass spectrometry on it on this single particle basis later. So I mentioned the hairdryer analogy where the bowling ball drops onto this hairdryer, and that obviously would be a bad thing. This actually happens in the atmosphere as well. These ice crystals can be so large that they come screaming in and they actually pit material off of the inlet. They act like a sandblaster. And that's something that we identified a few years ago. This is about 2004. We started to see a lot of spectra in these ice clouds that looked like this. we were actually starting to write a Nature paper about how stainless steel was found predominantly in ice clouds. I'm kidding about this. But this was a bit stunning that we were finding all this stainless steel in clouds. My boss at the time, Dan, actually did a quick calculation and realized that if there really was this much stainless steel in clouds, that it was more than the actual average amount of stainless steel produced in the entire world. So we knew that there was a problem. What we realized was that it was this sandblasting mechanism. And what it caused us to do was start coating these inlets with very structurally specific material. So we started plating these things with gold and titanium. And the reason we did that is that if you look at the mass spectra of something from a gold-plated inlet, you get this beautiful peak at 197. This is the single isotope of gold. It's really easy to edit that out of the data. You can imagine something like this could easily be confused with something like a mineral dust particle. And this was our reasoning behind going to this sort of advanced technique of building these new inlets and then also coating them with material. Okay, so I hope I've convinced you that we've come up with a way of separating these cloud elements out and a way of analyzing the particles that cloud was made out of are. We now need a way to get into those clouds. We need to get to the sample site, as it were. So we use the NASA B-57. This is actually an old Air Force bomber. It's capable of going to about 19 kilometers, so actually well into the stratosphere, the next layer of the atmosphere up. It has about 6 hours of duration. Oh, I should mention, this little piggy nose on the front, this is actually that CBI inlet that I was telling you about right here. And the mass spectrometer fits in the nose of this aircraft right here. This is able to carry a large payload of instruments. The old bomb bays of this aircraft have actually been retrofit with pallets that we can now put all kinds of instrumentation into. There's a single pilot and then a single co-pilot, so everything has to operate autonomously. This all has to sort of go in the aircraft and flip a switch, and then it has to run from that point forward. And the CBI Palms inlet combination was first flown in 2002. This was when we started realizing that there were these problems with stainless steel and artifacts. We've been trying to refine the technique, and I think we finally got to the point in maybe 07 and 11, just last year, where we're getting really high quality data from the flights that we're very confident of at this point. So with that, I'd like to tell you about this set of data that we got from 2011 in these so-called MacX flights. So the theory behind MacX was that I might be able to say that all cirrus, all ice clouds are undersampled in the atmosphere. We need to really know more about them wherever they exist. But one particular area of interest is the mid-latitudes. There's a lot of people that live in the mid-latitudes. There's a lot of industrial activities going on. There's also a high frequency of ice clouds. So there's a real lack of understanding the coupling between these things. So this was a set of flights out. If you're familiar with the Gulf Coast area, this is the Gulf, this is sort of the Delta. New Orleans would be sort of right here. So this is Houston right here. And the B-57 lives at Ellington Air Force Base near NASA Johnson Flight Center. So these are tracks that we took, and these are all sort of sampling cases of mid-latitude cirrus during March, April, and early May of last year. So you have to fly up to the ice clouds, get into the ice, find the ice clouds, get into the ice clouds, and then fly back home. What that means is that on average, only about a third of your flight is actually in the ice clouds. So it's actually a fairly small percentage. During that time, though, you get some thousands of particles that you characterize around the cloud, maybe underneath and on top of that cloud, and then some hundreds of residuals. Again, these are very tenuous, very thin clouds. So on a good flight, you might get some, maybe 1,000 particles that you characterize in these clouds. And then we integrate those over the course of the mission. I'm showing you 4 examples here. I think we had a total of something like 18 flights in mid-latitude cirrus. So some many thousands, 10,000s of ice nuclei. I'm going to contrast these mid-latitude cases that I just talked about with a couple cases that we did actually over the Gulf of Mexico. And these were very different cirrus clouds. These are things that were formed by subtropical jets. So these are cirrus clouds that existed probably for a long period of time, spanning out from the Pacific Ocean, kind of going over Mexico, and then eventually making it into the Gulf of Mexico area, where we were able to sample them. So with that, I'm going to dive into the results, what we found. So to do that, what I want to remind you is that we're getting on a single particle level, one particle at a time, a mass spectrum, a chemical composition. What we then do is, you would become very bored if I put up 10,000 of these spectra today, so I don't want to do that to you. Instead, what we're going to do is we're going to make this into a pie chart. We're going to take that particle, which I said is something akin to like a mineral dust particle in the atmosphere, and we're going to lump it into a category with all of the other particles that have those same spectral features. So this is outside of cloud. This is what the atmosphere looks like if you went up to 10, 12, 14 kilometers. The atmosphere looks something like this. there's a predominance of sort of sulfate and organic particles and particles that are due to biomass burning. There's lesser amounts of elemental carbon or black carbon. There's a bit of sea salt that we see, a bit of particles that seem to come from anthropogenic combustion, oil combustion, and then some mineral dust and metallic particles. You might think that this is a rather large chunk, this biomass burning chunk, and it actually is. And I'll remind you of something. If you remember the news from last year, especially in the springtime, the Southwest is still actually under very high drought conditions. There was a lot of biomass burning, natural and anthropogenic, that was going on in West Texas, Arizona, and so on. And actually last year, the whole depth of the troposphere was filled with these biomass burning particles. And we see that here. So there's a lot more of this on average. But the general trend holds that most of the particle mass in the atmosphere is sort of sulfates and organics and things that contain some biomass burn.
Would that abnormal biomass burning also signify abnormal amounts of elementary black carbon?
It turns out that this is a category that I'll show a bit more on in just a moment, but these are probably more akin to anthropogenic combustion particles here. Biomass burning has some tags like potassium in it that allows us to put it exclusively in this category. You're right, structurally, morphologically, it does look a lot like soot, but there's other salts and things associated that using the mass spec we can differentiate it out. It's a good question though. So on that special Gulf flight that I told you about, if we look at the residual particles in the cirrus cloud, it looks like this. You might think that this is exactly the same pie. There's actually a new little feature that comes in here, and this is meteoritic material, which we see very high in the atmosphere close to the tropopause. This is material filtering down that we don't normally see in the atmosphere as a whole. But otherwise, you would be correct. This pie looks very much like the outside of cloud picture. And this kind of tells a boring story, right? As I said, it's rather a smoky environment, but this is just sort of homogeneous freezing. This is this idea that you're forcing the system really hard, you're getting below minus 40 degrees, and everything just freezes. And you would expect to get a pie that looks like this. We've actually seen this a few times in all of the hundreds of clouds that we've sampled, this Gulf flight just being one example. What's interesting is if we compare this to all of the other flights, so this is one flight I said out of about 18 that looked like this. The rest of the flights look very different. When we were over the continent, not over the Gulf, the pie for outside of cloud looked like this. It looks largely the same, but you see that there's this large increase in mineral dust. One of the reasons is that this biomass burning at this point in time had sort of stopped. So now you have a lot of bare land cover. The wind comes by, and what does it do? It picks up and blows mineral dust into the atmosphere. So now we're seeing that the depth of the troposphere has a lot of mineral dust in it, in addition to this biomass burning. The result on the cirrus residuals was really striking, though. Now this pie of the cirrus residuals looks nothing like the outside of cloud aerosol. It's by far dominated by a minor amount of the aerosol, and that's the mineral dust. So these are what I'm going to just sort of refer to for the rest of the talk as sort of the dusty days, or the mid-continental, mid-latitude cirrus days. So again, this is, just to reiterate, this is consistent with heterogeneous freezing, not homogeneous freezing. This is what we saw about 18, call it like 1918, 19 out of 1920 different times. So the vast majority of the cases actually look like this, as opposed to the first sort of boring case that I gave you. Also, I wanted to point out that this is nothing new. Folks since the 1950s onward have known that mineral dust is a very efficient ice nucleus. I think that this just sort of supports that contention, but I don't want to give you the idea that we're sort of the first to sort of jump into this. So there's some interesting things to think about here if we drill deeper into this problem. And those things are, we can start them out with, well, what don't we see? What doesn't make it into the ice phase that we know is in the atmosphere? And one of the things is black carbon. So we only see a couple of spectra that look like this. It has this sort of characteristic pattern of 12, 24, 36. This is CN. So this is black carbon or elemental carbon with a bit of organic material on it. I should have mentioned that to support these mass spectrometry results, what we also did was we collected particles after that CVI and brought them back to, in this case, MIT to look at with an electron microscope. So we sort of wanted to see if there's a correlation between what we see with the microscope with what we see in situ in the atmosphere. And indeed, we only had 2 examples of particles that look like this. This is a fractal aggregate. There's these little spherules here. They have this sort of characteristic 40 or 50 nanometer shape, and then if we do elemental composition on them, this is almost pure carbon. So this is, again, this graphitic elemental or soot material. And again, this is material that's probably from an anthropogenic source, not from a biological one where you would get salts associated with it from plant material. So soot is noteworthy for its lack of abundance. I told you earlier about Ulrika's paper where she sort of theorized that maybe 1% or 10% of soot was a good ice nucleus and had this large climatic impact. It turns out it looks now like that was a bad assumption. Soot is actually not a good particle for nucleating ice. We don't see it a lot. In fact, over the course of all these studies, less than 1% of the particles in any one cloud or any one cloud mission have ever been soot. It just doesn't look like there's a lot of these, if they exist, good soot IN in the upper troposphere and lower stratosphere.
So do you ever turn the CVI off so you're getting the interstitial air, and do you see the soot in the interstitial air?
Yeah, we do actually. So what we actually do is, I didn't describe this just for sake of time, but there's the CVI inlet and then there's a dumb inlet. There's just a simple inlet next to it. And we have a valve. We just switch between those two channels. So we can look outside of cloud with the dumb inlet, and then we can look at the interstitial inside of cloud. You still have to subtract away these artifacts from sandblasting, but indeed that's the case, that you find the soot in the interstitial slightly enhanced because it's not finding its way into the ice phase.
But it's still not as big as what the theoretical slide you showed earlier from the other author, the supposition of 1% or 10%.
That's correct,
okay.
Yeah. So what else don't we see? We don't tend to see a lot of biological material. This is a paper by Carrie Pratt that appeared in Nature Geosciences a few years ago. And they were looking at a very specific type of cloud, a lenticular cloud, which is coupled to the boundary layer. And they seemed to see that about a third of the time there was something like biological material nucleating ice in these clouds. They did some mass spectrometry on those particles, and they seemed to think that this material had sort of a characteristic fingerprint. And I'd be happy to talk more about this later. But just to go through this very quickly, they pulled out some markers related to phosphorus for what they thought was biological material. So we actually went back into our data, and remember, there's many thousands or 10,000 of these ice residual particles, and we only found 3 that might have been associated with biological material. We did the same with the electron microscopy, and this is the only one that we think might be associated with biological material. At this point, you might be, how would you come up with this being biological material, right? I mean, this could be just about anything. It turns out that we had a reason, or a couple reasons, for thinking that this one particle might be biological. These are electron micrographs of fungal spores. There's a morphological similarity, but also if you look at the chemical composition of this particle, it has all of the right elements for being something like a fungal spore, including that phosphorus peak, which you can see right here. So this really probably was something like a fungal spore at 15 or 16 kilometers in the atmosphere. So the point that I'd like to make is that when we look at cirrus ice residuals, biological material is very rare. It's actually much, much less than 1%. One of these examples, maybe 3 in the mass spectrometer. I'm not saying that biological material is not a good ice nucleus. In fact, I think that there's a lot of evidence. Daniel has done some very nice work on it, that it might be an extraordinarily good ice nucleus. In fact, it might be so good that it never really makes it out of the boundary layer. As soon as it sees the first hint of low temperature and high humidity, boom, it nucleates ice and it sediments out. It just doesn't look like it's present in high abundances in the UTLS region. It doesn't make it there to participate in cirrus ice formation, at least not from the ice clouds that we've seen over the mid-latitudes. So this would be a very boring talk if I kept going through what we don't see in the atmosphere. So I should probably tell you what we do see. We see a lot of mineral dust. These are 3 examples. This is something like a bare mineral dust particle. I hope you can see this in the back of the room, but there's this capsule around this. We can look at the composition of this particle, which I'll show you in a moment, and then this. This is an organic coating. So this is something that's picked up organic material on its coat. In this case, you can see this little splotchy pattern around the mineral dust. This is something like a salt coating that was on the particle, probably ammonium sulfate. It hit the electron microscope grid, it splatted out, and then sometime later it effloresced, it crystallized into this little halo around it. This is sort of a well-known phenomenon for looking at electron microscopy. What's noteworthy is that by far the majority of the mineral dust that we see in these clouds is bare. It doesn't have coatings, even though in the background atmosphere, this is about 1/3, 1/3, 1/3. Those are rough numbers, but it gives you an idea. These are about equally proportioned in the atmosphere as a whole. But by far, what we see in the cloud is the bare mineral dust. The chemical composition of these, I'd just like to reinforce, these are really like aluminosilicates. That's what the compositional diagrams say, and that's what the mass spectra say of the single particles as well. So I think what's going on here can be envisioned in that phase diagram that I showed you at the beginning of the talk. And now, just to confuse you, I've flipped the axes so that this is the highest temperature and this is the lowest temperature. And this red bar here sort of delineates where the cirrus cloud formation is going on. And if we again think of this parcel of air moving up, cooling off, and rising in relative humidity, a number of authors have shown that the most efficient ice formation mechanisms are deposition nucleation, and they preferentially appear to occur on bare mineral dust, where that water vapor can sort of see the surface of the mineral dust. They knit together on that surface and form ice. For condensation freezing, it appears a bit delayed. Most of the data show that once you encapsulate a mineral dust particle with an organic or with a salt, it delays the onset of nucleation. And you might remember, you might know some of the authors that have done some of these studies in the past. So what else do we see? We actually see a lot of anthropogenic material. And I think that this is what I'd like to spend the rest of my time on today. And one thing that I'd really like to hammer home as a conclusion of this. These are a couple of electron microscope examples of very strange particles that almost certainly come from anthropogenic sources. This is a particle that's almost entirely zinc oxide. This is a particle that contains a lot of silicon, carbon, but also tin. And it's knit together in this fractal pattern that implies a high temperature source of formation, something like a combustion process, just like you'd see for soot.
Excuse me, what size? Size?
Oh, I'm sorry, I should have mentioned that earlier. If I show these at all, this is a 2-micron block here, unless otherwise specified. Yeah, thank you for catching me. I should have mentioned that much earlier. In total, during these mid-continent or mid-latitude flights, 10 to 25% almost of particles were anthropogenic in origin. And I denote that by saying they contain something strange, something that you would not normally expect to see in a mineral dust particle or other particle. I'll show a few more examples. This is one of my favorites. This is a mineral dust particle right here, but it's not entirely natural because there's inclusions of lead and tin on the surface. It's almost like it passed through a source region where lead and tin were being emitted, maybe a smelting source or something like that. And these little particles sort of knit onto the surface of that mineral dust particle. And these all acted as ice nuclei in the atmosphere. This is a mass spectrum of a particle of the same sort. It has peaks here and peaks here. Does anybody actually, do you remember your freshman chemistry? Does anybody, especially any of the students, remember what 107 and 109 are as isotopes? No one? Everybody's going to be shy today. So this is actually silver. What's actually interesting is that you then get this sort of, this triple peak over here, which is split from this by 35 or 37. This is chlorine, this is silver chloride. I hope everybody won't be shy. Does anybody know what silver chloride is used for? There's a couple of industrial applications of it.
It used to be in photography, but no more.
Yeah, it used to be in photography, but not anymore. It's actually still used as an electrical conductor. We see particles like this rarely, but they're more abundant as you go higher in the atmosphere and lower abundant as you go down. We actually think that this might be a particle source from spacecraft ablation, believe it or not. You guys probably read about the UR satellite that came back. That's a huge pulse of many tons of material in the upper atmosphere where there's not many particles to begin with. These things burn up and then the little primary particles that are burned off fall down through the atmosphere. So I'm not certain that this is the case, but we actually see some particles like rare particles of silver or gold when we're not using these special inlets, or things like silver chloride that have a higher abundance as you go higher, implying a top of atmosphere source. They also appear, some of them, to be good at seeding clouds.
What's the meteoritic source? Do you have
Oh,
meteorites?
It's meteorites, yeah, absolutely. So there's several tons per day of small meteorites that come in, and they hit 100 kilometers up in the atmosphere. They see atmospheric friction. They start to burn up, and they form small primary particles that rain down every day.
So you don't think that would be meteoric? I mean, figure out the tons of silver you need to get that concentration, the same calculation you did for stainless steel. It's
So
hard.
this is a single particle, and I'm just showing it as an example.
N
of
equals
what it is.
1.
Yeah, n equals 1 out of 10,000, right? So what I will talk about is the most abundant one, which is lead. Lead is the one that we see most frequently of all of the anthropogenic materials. In fact, it's 13% of all spectra. And I just want to remind you, this is implying that 10% to a quarter of all cloud-forming particles of these glaciated clouds have some anthropogenic origin. That's a huge lever arm on climate. A few more slides on the role of lead as I start to finish up here. This is the lead peak at 206 and 208. So let's just launch into a discussion. These are different lead ice-forming particles in the atmosphere. And when we started to present this data, it was treated a bit critically. Some people said, well, you're doing mass spectrometry here, and there's a lot of things that sort of could exist at the mass spectrum at 206 and 208. So are you really sure that this is an anthropogenic material and that it's really lead? Well, what we actually have the resolution to do is to blow that region of the spectrum up and look at it with higher detail. So what you can see is that there's peaks here actually at 204, 206, 207, and 208. If you go back to something like your freshman chemistry handbook or something like the CRC, you can see that the peak at 204 is about 1% of the isotopes, 24% at this, 22% at this, and about 50 at this. So this is not a high-resolution mass spectrometry technique, but what we can do is pull this out, and I can say this peak is about twice as high as these two, and this is something like 1% of the total area of these peaks. So this really is lead. This is not something else that just happens to coexist on the spectrum. Something like 10, 13% of the time in these ice clouds, we really are seeing lead. It really is lead, and it really is from an anthropogenic source. I'll talk more about that in just a moment.
That is a very clean part of the spectrum you're looking at, and I'm just wondering how much misidentification you might have where things are much more crowded.
Yeah, I would totally agree with that. I think that there's a lot more ambiguity over here, and you can think of common things like calcium oxide and iron, which coexist at 56, and I think you have to treat those a lot more skeptically with much larger error bars. We are lucky in this case to be talking more about something that is in a clean part of the mass spectrum. So I totally agree with your comment. And this would be an exception to, I think, this lower mass portion of the spectrum here. So where does this lead come from? Well, this is probably the most recent EPA report on lead, and I apologize for the folks in back. I can provide this reference if you guys would like to see it. I realize this is going to be too small. A lot of this comes from so-called area emissions. This is lead that was put down as leaded gas in the 1970s. It was put down in the arid places like the Southwest. When the wind comes along, just like we were talking about earlier, it picks that mineral dust up and puts it back into the atmosphere, along with any lead that might have bound to it. So most of the lead, the largest single source is these area emissions. Old lead that's recycled through the atmosphere, maybe many tens of times. Believe it or not, I was talking to John earlier today, we both fly, and we know that the gasoline in light aviation, general aviation, is still leaded. It still uses old engine technology. It still uses leaded fuel. There's a special dispensation to still burn this leaded gasoline. There's a bit in coal. This one probably now has surpassed this one just because there's more coal-fired power plants being built, especially around the world in places like Asia, India, China, as well as in the US. And then some contribution from things like smelting and other industrial sources. So I think I heard it mentioned earlier, but there were actually experiments in the late 1940s by some folks that wanted to make ice clouds. They wanted to make it rain in certain places. This was pioneered by Bernie Vonnegut right here. If that name sounds familiar, this is actually Kurt Vonnegut, the author's brother. Talk about a stupid family, right? You got one guy that's doing cloud seeding and one guy that's writing books. So this was really true. This was stuff that was done in upstate New York at one of the universities. And he did like a Thomas Edison type approach. He started going through crystalline structures that looked like water ice, trying to make cloud seeding elements. And he came up with silver iodide as something that matched the hexagonal structure. Something was found that was even better, actually by the Russians, which was lead iodide. And the Russians figured out that they didn't have to make an entire particle out of lead iodide. They could do an inert particle here, and then just put on a little bit of material that was this active ingredient, this lead iodide that had the right crystalline structure. So a lot of people have said, oh, well, this was really nice of the Russians. What they were trying to do was make sure that they didn't, sort of poison people with their cloud seeding by not putting too much lead into the environment. That wasn't it at all. If you read these papers, they were trying to save money. Lead iodide was relatively expensive. This inert particle they would make out of cement just cement powder, and coat it with lead iodide. And that was their ability to do cloud formation. And their motivation was actually not to make it rain where they wanted to. They actually started doing this to make it not rain on their May Day parade. They would ring Moscow with artillery and fire this material up into the clouds to not have it rain on their parade. So I'm not making this up. This is really true. I can give you the literature. I mean, it's like science. You know, the truth is stranger than fiction. So I think what's happening here is that we're unintentionally doing exactly what the Russians were doing intentionally. Again, just to bring you back, this is a particle of mineral dust that went through a lead source area, and it picked up something like a lead-containing particle, a primary particle on the surface. If you're paying attention, this particle, an inert particle with a capsule of something that's an extraordinarily good ice nucleus, looks a lot like something like this. And we see this time and again in the electron microscopy, and I think it's supported also by the mass spectrometry. But again, a semi-inert particle with these little lead particles on the surface. And if we do energy dispersive X-ray on this, we find that all kinds of lead states are possible. We see lead sulfides, lead oxides, lead halides, and even some organic lead compounds form these particles. You know, it probably just depends on how they were emitted, what the source was. So with my couple minutes remaining here, I'm just going to wrap up with some conclusions. I think that we had problems in the past, most of which have been overcome by new technology. And I think that what I've been trying to show is that this counterflow virtual impaction, when it's combined with this single particle mass spectrometry and this collection method of electron microscopy, is a really powerful tool to elucidate these aerosol cloud interactions, figure out what these special particles are that nucleate us. I don't want to leave you with the impression that aerosols are the only thing that are important. In fact, I think that dynamics are critically important. When we have these homogeneous freezing clouds, the aerosols are essentially unimportant. You saw that the pie chart looks just like the particles that were already there. The particles don't really play a role in that. Dynamics are what's important, and the parcel history of that air mass. There are a lot of cases, the majority of cases, where the particles are important. And that's true of these clouds that I showed you where heterogeneous freezing is inferred. We can go further and say that there's certain material that's not important in the upper troposphere. Soot is not important. It's just not of abundance for good soot ice-forming particles if these exist in the atmosphere. It's much, much less than 1% of the so-called ice residual particles. Biological material is probably incredibly important lower down in the boundary layer where it's emitted. It is not abundant or significant for cirrus cloud formation in the upper atmosphere. Again, to reiterate, these good ions are probably gone. Probably the take-home message is that mineral dust is important. Anthropogenic material is also important. And the reason anthropogenic material, the ones that I showed you at the end, are so important is that that's the lever arm that we, as mankind, have on climate. As we put more and more of these particles into the atmosphere, we are changing ice cloud properties. So we know that we're emitting greenhouse gases. That's well understood and well known. It is less understood that we are also putting particles in there that are affecting clouds that are somehow offsetting, to some extent, the climate change due to greenhouse gases. They're a negative forcing agent. And what I'd like to say is that the work that we do at MIT and the work that Daniel does here is still critically needed. You know, this sort of points us in the right direction of what's important in the atmosphere, but really drilling down and understanding the exact activation thresholds, the relative humidities, the temperatures, the activities of this material is something that we can't do in the atmosphere. It's something that you have to do in the laboratory with experiments like what Daniel runs. So with that, I'd like to thank you for your time and just ask if you have any questions. I should let you take charge.
Wow, all right, let's show
So do you
this.
think if you were looking at cirrus clouds closer to the poles or over oceanic areas, you might see some evidence of marine biogenic particles? I mean, you see silica, and of course there are lots of particles in the ocean. So is part of your conclusion a result of where you've looked?
I believe that's the case. I believe that it's partly where we've looked. There's two majorly undersampled regions of the Earth's atmosphere, especially with respect to clouds, and that's the high latitudes, where production is probably more likely, and the other is the southern hemisphere, where you have a lot more ocean versus land mass, a lot less of these mechanically generated particles from the continents that may dominate in the northern hemisphere. I think there's one other place that we could go that might shed some light on this, and we actually have a bit of data from that 2002 mission, which is convective activity over the oceans, where you might have this sort of vacuum cleaner sweeping material out of the marine boundary layer, putting it high up. And we do think that we see a lot of sea salt, and it's actually a project that we've talked about working on together, is maybe revisiting that old data and seeing if there's something like marine organisms in them. I also think that high latitude studies are another way to go. Yeah, that's a good point.
Art?
Nice talking, Dan. Two questions since I'm a BC soot kind of guy. I noticed on your cirrus residuals over the Gulf, you showed no BC. You just lumping those in the biomass part of the pie chart?
In general, yeah, if things fell below a few percent, they don't show up well on that graph. So something like soot in the background atmosphere, we tend to see varying between 1 to 5%, which would just barely show up on those very crude pie graphs. So that might be the answer. I think in all places it's about 1 to 5%.
All right. However, one thing I was very surprised about is when I showed the TE, I think it was TEM of your soot, it was fractal. That tells me that it's not aged. And I wonder if, in fact, you're not sampling soot, say, from commercial aircraft. And then that begs the question, is that why it may not be acting as good IN? Because it's not got that coating similar to what's necessary for coated soot to become good CCM. What are your thoughts and comments on that?
Yeah, I think that that's a good point, actually. And I'm going to answer it in one of two ways. That was a surprising soot particle. If you noticed, it was completely uncoated, which is actually fairly frequent in the upper troposphere because the coagulation rates with some of these coating materials is relatively low. There's very little of that material around. It was also very big. If you notice the scale on it, that was a couple micron soot particle.
I didn't catch that.
It's a very large one. So people have asked, are we missing soot because it's below our size threshold range? Well, it turns out that there's very good data on the size distribution of these ice-forming particles, both with our instrument and others. And it looks like they fall down significantly below a few hundred nanometers in size. So the soot is probably sitting at a size mode that's smaller than what tends to be found activating these cirrus clouds. So again, if it's there, if it's a good ice nucleus, it just doesn't seem like there's a lot of that material. And part of that may be because it's small. It doesn't have a lot of surface area to act as this depositional site for nucleation. Joe?
Yeah, Dan, for the electron microscopy photos, how did you bring the particles back? Did they go through the counterflow impactor as well?
Yeah, so essentially, I probably should have put a flow diagram on, but just for the sake of time, I wanted to stay away. So what we have is a flow splitter, basically a Y after the CVI. So we have essentially the same residence time, and when we're sampling off of the CVI, we are taking part of that flow and impacting it on electron microscope grids, and taking part of that flow to the single particle mass spectrometer. So we can actually correlate flights and a bit of time information.
You seem surprised that there's a relatively high percentage of uncoated dust particles, and I was just curious, is there any possibility with the counterflow that you're somehow sublimating or getting rid of some of that coating?
Yeah, no, I think that those are actually both valid concerns. So if somebody didn't hear it, the idea was that, by doing the electron microscopy, are we somehow getting rid of coating material? It's a valid concern, but I don't think it's really legitimate for a couple of reasons. We have done calculations of what would evaporate at this change in temperature, and you are certain to lose some things like nitric acid. If there was nitric acid on that particle, it probably wouldn't even make it to the mass spectrometer, much less survive on the electron microscope. I showed electron microscope data. That correlates with the mass spectrometry data. The mass spectrometer as well doesn't see the coating material with higher than 10, 20%. Whereas if you look in the atmosphere, it's there at about a third. So there really is this change when you sort of fractionate in these ice clouds. Yeah.
I assume your flow dynamics are pretty critical to air density. And what's the practical vertical range over which all of this works?
Yeah, so again, for sake of time, I didn't explain a lot of this, but what we actually do is we flow an isobaric inlet upstream of everything. So what we try to do is keep everything constant from a few kilometers altitude up to our max altitude of, say, 20 kilometers by going through an isobaric lens. So dropping the pressure on everything down to a fixed point, which is less than our highest altitude point. And then we do our CVI, and we do our analysis. So we actually don't believe that there's a big change. The sacrifice we make is that we consequently have lower transmission, less particles that we look at lower down, so that we try to equate everything to the highest possible altitude. Yeah, so we run that at, if it's of any interest, I think it's like 40 millibars.
You can really cover most of the atmosphere up to the stratosphere.
You can.
Okay, Sultan?
So given the anthropogenic contributions you found in these particles, so how much more cirrus do we have now compared to 100 years ago?
Yeah, that's a good question. So again, if you guys didn't hear it, the question was sort of the temporal change in cirrus. It's actually more complicated than that, and it's something that we've started to look at. I think that the implication is because of this lead, that cirrus may have actually been more abundant in the 60s and 70s, and now we're back at a point that may be closer to sort of a pre-industrial or pre-70s time. There was a factor of 10 more by mass lead emitted in the 1970s, the late 1970s, than there is now. And this is a study that's been sort of on the back burners to try to look at old cloud fractions. The problem is satellite data doesn't go back that far. So what we would have to do is probably go to sources like cloud atlases, visual identification of cirrus. And it's actually a very difficult task, but one that we've thought about doing. I think clouds, yeah, we're probably more abundant in the 70s. That's a signal that we might be able to pick out. Right now, the cloud fraction is probably still higher than pre-industrial, but not like not like a factor of 2 or 3. And some of that is probably in subvisible things that are very hard to measure. But it's a good question, and one that I think is right on the cutting edge of what we can do now.
Just to comment on that, but you have also higher air traffic, and you have contrail-induced cirrus, so that plays also into that. Yeah, cirrus cloud cover.
Yeah, the change in water vapor in the upper atmosphere too.
Yeah, I was curious if you've given any thought to trying to sample aerosols from volcanic eruptions as a possible source for your red.
Yeah, it's a good question. So the one that heightened awareness of this was this, what they call the E16 volcano, E in 16 letters I can't pronounce afterwards, the one in Iceland. So we actually got some of that dust, and we've been running it through the cloud chambers in the laboratory. It actually looks like volcanic material in general is not a very good ice nucleus. And Daniel's actually former group at ETH has done some of that research as well. They collected some of that material, brought it back to the lab, and looked at it. We've started to study it, but it also looks like if you track those volcanic plumes sort of downwind, they do tend to form ice at some point in time, but not at particularly high temperatures or low saturations. So relative to mineral dust, it's actually a rather poor ice nucleus.
Bruce?
I want to ask you something beyond your talk. There was a paper last fall or summer, but I don't know if it's Wiggly or Wrigley, about if we replace CO2 inefficient coal with gas, forgetting the leakage rate of the gas, you'd be knocking down the aerosols enough, presumably sulfate aerosols, that you wouldn't have a net, you wouldn't have any improvement. If anything, you might even have some worsening of radiation balance. I was wondering if you could make some comments related to that.
Yeah, that's an interesting question.
That makes sense.
Yeah, Daniel and I'm laughing because Daniel and I were talking about this on the way over, actually. I have to qualify this by saying I'm not a policy person. I'm familiar with the work that you're talking about. Indeed, it is the case. If you knock down particle sources, it is very likely that you consequently raise temperature because you take away some of this masking effect. You're taking away a negative impact or a negative forcing and leaving the positive forcing or some fraction of it behind. There's a lot of folks that have written a lot on this, and I'm not an expert. There are other factors that come into this as well, which is human health, because we didn't even talk today about the fact that there's increased asthma and increased deaths due to inhaling these particles. So there's very good reasons to clean up particles, as well as consider the impact of those particles relative to CO2. Of course, I fall on the side of thinking that we should probably try to clean up in both areas, but pay attention that there are going to be these unintended consequences, that you can quickly change particle densities. There's examples of that too, like when the Soviet Union collapsed, almost overnight, the particle concentration went to 0. And there's records that you see the temperature spike in those regions in Eastern Europe by a few degrees because they took away this global direct aerosol effect. So we should pay attention to that, but there's other factors, things like human health, that also have to come into play. So I don't know if that answers your question entirely, but
I was just wondering if there's enough, based on your understanding, if there's enough coal aerosols in the ocean
it's good.
It's Friday.
It is, and it's getting late too.
All right. That's last question,
Yeah, Bob,
then we finish up here.
You're not going to be able to answer anything else.
You didn't mention anything about the mineralogy of the minerals that you actually are seeing. Do you have any information on that that might actually give you more insight into the source of that material?
Yeah, we've actually been working on that project, and I didn't show any mineralogy data today. That's absolutely true. There is an impact of the mineralogy, and it appears to be something like the crystalline structure of whatever that mineral is and how it matches up with the lattice of ice nucleation. And there are a number of groups. I don't want to make it sound like we've been the only ones doing this. I think you've worked on this a bit, and Daniel's old group has worked on this. But it does look like certain source regions have better ice nuclei or generate better ice nuclei. The Sahara is one region that has mineralogy that the aluminosilicates that come off of there are very good ice nuclei. So there's some correlations. What we've been working on is trying to back out of these. When I show a mineral dust particle, is trying to say, where did that mineral dust particle come from? And in general, we seem to be able to do that. With a very broad brush is say where those particles are from. And again, there's these certain source regions, the Sahara being one that generates extraordinarily good IN. The Mongolian Plateau is another example. Yeah.
All right, then let's come to a conclusion. Thank you very much for the wonderful